Hi, everyone. My name is Daniel Wertheimer, and I'm a data scientist at ABSA. And today I'm going to be taking you through my talk is titled Accelerating ML Model Deployment Through Open Source Development. And this is kind of a lot of the work that we've been doing at ABSA in utilizing and building open source tools to put our machine learning models into production. So just quickly, who I am. My name is Daniel Wertheimer. As I said, I'm a data scientist and machine learning engineer within the group Chief Technology Office at ABSA. My specific team focuses on servicing the retail bank with a lot of the AI capabilities that they kind of want to have. I've got all my socials on the right-hand side. You can contact me on any of them if you need to, but I'll have them in at the end of my talk. So to preface this talk, I think it's important to talk about the state of AI. And this was in a McKinsey State of AI talk from, paper from 2020, where only 22% of companies that were interviewed were attributed 5% of their earnings to, or more than 5% towards AI, which is a really small number. If you think about it, it's like companies aren't getting a massive return on AI. And if we go to this kind of view of value generated and analytics maturity, and you'll see this in a few different places. I think Gartner is the one that made it famous, but we want to play in this kind of predictive modeling space. This is where AI kind of sits at the moment, and optimization is this idea of like hyper personalization, etc., for customers. And that's where this massive value is. But AI and data science, at least within the South African context, is very much playing in the predictive modeling space, unless you're kind of like a fintech that doesn't have a lot of legacy behind you. But according to those stats and according to what we used to see, is that it looks a little bit more like this, where the value generated as you kind of grow in your maturity doesn't increase all that much. And the reason that this happens is that a lot of the work that's done in data science and AI, at least at the moment, happens on the side of the desk. And what I mean by that is, like, in a Jupyter notebook or something like that, it's not necessarily productionalized. And that's where the majority of value from your data science is going to come from, when it's actually impacting end users. So the operationalization of these kind of things is incredibly important. So instead of having a look at this in terms of 2 dimensions, it's important to look at it in 3 dimensions, where you have value, analytics maturity, and then the degree of operationalization. And we want to play in that kind of upper echelon of what it means to be fully operational, fully mature in terms of our analytics and generating maximum value. But the question then is, what's stopping us from getting to that fully operationalized state? And it largely comes down to, at least within emerging data science capabilities, is that there's a difference between academia and industry when it comes to how data science is done. In academia, and this is in no way to bash academia, without academia, it would be near impossible for us data scientists to do and build the kind of robust models and performance models that we do. But it doesn't serve the purpose of what we need in industry. And what do I mean by this? So in academia, we aim to spend 6, 9, 12, 18, 24 months working on a specific problem to increase accuracy by a small percentage. And then we write a paper, which can take another 6 months, and then we get it published. And that's like a great achievement, right? If we can aim to do this. However, if it took us, 9 months to get a model in place, to kind of eke out a tiny bit of revenue, business is going to be really, really, really upset. And again, remember that the academia stops at the model evaluation process, whereas, as I mentioned a few slides ago, we care about actually putting that into an operationalized state. So we need to take it a few steps further, and that's kind of that's where a lot of the time and effort comes in, and it's quite tough to do that. And to put a model into production, there's, you've got all these source systems, and the data scientist needs to kind of build a model and do all this feature engineering and all their stuff, and then it needs to be served to the end users, right? And this is what we expect from data scientists. This is why they're kind of deemed as this unicorn that has all this exposure in computer science and stats, and they're liaising with the business, and that's how they're going to add value. But it turns out that for data science solutions to make their way into production environments, it's not just one person that does data science. It's a team. And that team requires data scientists to, like, obviously to build the models, etc. Requires data engineers to make sure that pipelines are resilient, so data gets from point A to point B without us having to worry about it. DevOps for automated deployments. I apologize for the airplane above me. It requires solution architects to design, if it's a complex solution that hasn't been worked on before, then we need someone to help architect that. So we've had to do that with some of our real-time use cases. Process engineers, business analysts help understand business flows and business data. It's really complicated. And we often put this onto one person to do. And it would be nice if it was one person's job to do all of this. It's unrealistic, but how can we make it easier for data scientists to take away a lot of this complexity around putting models into production? So I guess starting at the actual business case and then moving it into production, how can we make that process easier for the data scientist, and also require a lot less resources in terms of people hours from other roles, such as your data engineers and your DevOps specialists, to get it there? And that's a lot of what we've been doing in terms of the model analytics platform and the cognitive platform that we're developing inside of ABSA, utilizing a lot of open source tools and also putting out a lot of open source tools. So let's head over into the model analytics platform. So in terms of the model analytics platform, we have a unique problem. Actually, it's probably not all that unique at ABSA, where we've got I think it's any legacy entity will have a lot of these problems. Again, ABSA is an amalgamated bank of a few other banks within South Africa. So we've got a lot of legacy. We've got a lot of different source systems that have a lot of different formats. So we have to consume data from CSV, Parquet, mainframe systems, all in different places with different cadences. So we have daily, hourly, weekly, monthly tables that we need to ingest. And we also don't know when data is available, right? So like mainframe data is available when it's available, which is kind of a weird thing. And that's that process of coordinating this. So if you consider the batch world, which is where a lot of what we do is playing right now, we do have some real-time use cases. The coordination of all these things is quite difficult, especially within the landscapes or technology landscapes that we have at ABSA. So the coordination of this is imperative for us to operationalize our data. So for this, we've developed a tool called SyncWatcher, which runs on Hadoop and Spark, and it helps us coordinate upstream and downstream data sources. And what's amazing about this tool specifically is that while there's a lot of code that's been built by data engineers, what data scientists have to do, or business analysts can even do this, is it's entirely configuration driven. So you just need to point towards tables. You need to define certain things around, what our partition columns are and update formats. And we don't have to worry about any code at all. It's very, very simple to use. So some of the benefits of this are things that like bookkeeping. So SyncWatcher keeps a record of input and output columns, input and output records, and it looks at tables historically as well to determine whether data has been updated for previous historic dates, and if it's been missing, it can rerun downstream processes. So again, there's this upstream and downstream dependency management that SyncWatcher also does, which is really, really great. Especially, we have instances where we read from tables that have a kind of they're aggregated from a bunch of different source systems. And if one of those source systems is missing, sometimes that table loads, which can be an absolute nightmare for downstream processes because let's just say that one specific type of customer is no longer in that data set. When it gets to the end stage of the model, that customer is not there. But what SyncWatcher will do is it will say, tomorrow, let's say this table runs, it will look to say, is this table still got the same number of records? If not, let's re-ingest that and rerun any downstream processes to update them. So that's one of the great things about SyncWatcher. And then again, it's pretty much data source agnostic. So we can read from multiple different data sources. So whether it's Parquet, MongoDB, relational databases like SQL or Postgres, any of this can be scheduled through SyncWatcher. So we've kind of solved the case of getting stuff from data from our very messy source systems into our data science environment. But the question is, how do we then take the data from our data science environment after it's gone through this process of, excuse my cat's trying to climb through the window. The joys of working from home, all right. So how do we move the data from our data science environment into our Hadoop and Kafka, or at least our strategic environments? And the way that we've done this is that we developed a tool called Py2K. This is actually open sourced. So this is in the open source domain on ABSA open source software on GitHub, which I linked at the beginning and will link at the end. And the idea of this is to support real-time streaming on Kafka from Python and keep data scientists doing data science. And how do we do that? So if you've ever tried to put data from Python onto Kafka, for example, so Kafka is a real-time streaming platform, you'll know how difficult it is. It's 1,000 to 300 to 1,000 lines of code. If you want to make use of things like the schema registry, to strongly type your output, there's a lot of jargon that you need to know. The security protocols, etc., are quite intense. So it's really, really not user friendly. And often this is the job of a data engineer or a DevOps specialist to help him come in here and solve this. We've managed to do this in 5 lines of code. Actually, if you ignore imports and you don't make the code look pretty, it's 3 lines of code, which and this solves almost every use case that we've had. And again, because we're actively using this, it's being actively developed, and we're constantly improving it. So again, this is one of the pros of open source software, is that we constantly have this improvement. So Py2K solves this notion of from the data science environment into Hadoop and Kafka. I know I haven't quite mentioned how that gets onto Hadoop, and I'll do that just now. But what I do want to touch on is our real-time use cases. So how do we go from Kafka to Kafka/Hadoop? And the way that we've done this is that we've developed something called the cognitive platform. And the cognitive platform is a microservices-based approach. And the reason it's called the cognitive platform is because it was originally designed for our cognitive workloads. It kind of stemmed from this image, text, video, audio use cases that we had. And so this is a little bit more complex because it's an entire platform for data science. And the reason that we built it is that we needed something to make it easier for data scientists to build their models on real-time data sources. So the idea here is that these were some of the drivers that we had around it. We needed it to deploy it onto the cloud. We needed to be able to deploy up to, I think, about 6 million models. We need to make predictions in real time. They need to be super low latency. So fraud was one of the use cases. We needed to do this within, I think, 100 milliseconds. We needed to make predictions with our models. So there were quite a lot of drivers, and this is that notion that we needed a solution architect. But if you can build it once in a reproducible way, you have this really nice way that you can, or pattern that any data scientists can use to kind of follow and move their models onto real-time data sources. And all that the data scientist really has to do in this case is serve their model as an API. And because there are tools like Fast API that make it very easy. So I think Fast API, you can probably get an API up and running with about 25 lines of code. And again, it's still within the Python environment where data scientists are comfortable. You kind of increase the time to production. So some of the use cases that we've deployed on the cognitive platforms, again, cognitive and traditional services that we currently have. We've got facial recognition and document analysis. So these are for things like KYC, know your customer. And then there's more traditional use cases like Planix, income prediction. Digital fraud is the one that I mentioned. So the thing though is that, as I've mentioned with Py2K and the cognitive platform, is that we need to, we've got our data on Kafka now, which can be consumed by some systems that are consuming data in real time. But how do we store our data? And that's where Hadoop comes in. And that's what our other strategic data source. So we need to move our data from Kafka onto Hadoop. And this is also quite a difficult process, especially with Python. You want to build consumers, and it's the same story. If you do it in Python, 300 to 1,000 lines of code, get it on there. It's quite a mission. And that's where one of the other teams within the bank, the data tooling team, has built something called Hyperdrive. And Hyperdrive is a tool to manage ingestion from Kafka onto Hadoop with Spark. And again, unlike SyncWatcher, which is config driven, I guess this is also config driven, but instead of having to do it through some kind of text editor, this is all user interface based. So you can just create a workflow. You give it so each workflow has a unique kind of string attached to it, which you just need to send off to Hyperdrive and say, the data is ready, please ingest it. And Hyperdrive will be like, cool, I'm ingesting this into this location, and it goes, and it just runs. And what's great about it is that you can copy existing workflows, and all you need to do is change a few parameters. And again, takes away a lot of the overhead of the data scientists so that they can own that full end-to-end process. And this is something that we advocate for at ABSA, is that our data scientists should be able to own the end-to-end process. Obviously, a lot of it doesn't make sense to. So, the data scientists shouldn't be responsible for data being late, but they should be responsible for their models and making sure that once the data is landed, their process from feature engineering to putting the models into or the results into a production database or into some API that is owned end to end. So that kind of fulfills the entire end-to-end life cycle of what it means to be data science at ABSA. But the question is, what's next? And for us, that's automated deployments to the cloud. So we are doing a lot of automated deployments already through enterprise GitHub, but something that we've actually got within the broader Chief Technology Office, and you would have seen our CTO, Andy Baker, post about it a while ago, is a tool called Subatomic, which we are looking at. I think that they are looking at open sourcing it. However, the architecture of it is within, I guess, the open source domain, given that it's been posted online. And the whole idea behind Subatomic is that it is a platform agnostic container deployment, I guess, framework or platform. So what we do is we deploy our models on Subatomic as containers, and regardless of whether that's on our local, or at least our on-premise Kubernetes, or we move to AWS, Google Cloud, or Azure, we don't have to worry about that complexity. It's all managed by Subatomic, and it will deploy it to dev, UAT, prod productions, the prod servers, with different promotion criteria, etc. So that's something that we're looking at incorporating for our models. So a lot of the cognitive platform, actually all of the cognitive platform models are deployed on this. So the model analytics platform, we're working to get it there. The one thing, though, is that there is a missing link for us in terms of the model life cycle, or at least the data science life cycle. And that, in a lot of cases, it looks like this, where you've got some data sources, you do some feature engineering and modeling, and then there's some output. But it turns out that the missing link here is this features component, right? What we're finding more and more is that because we play in the same domain, banking, that is, at least at ABSA, we tend to make and use a lot of the same features across projects. And if we had a centralized feature store with feature owners, it would kind of accelerate our deployment and model building process considerably. So just like as an example, when I first put my first model into production, it took about 9 to 12 months to operationalize. It was a regulatory model, so it did need to pass a lot more checks, but to actually put it into production was a very long process. With the next person to do this, as we started putting down these criteria and these patterns for putting models into production, that cadence of deployment of models increased considerably. So it went from 9 to 12 months to 6 months to 3 months to getting a POC out within 2 to 3 weeks, like a proof of concept within 2 to 3 weeks. We're able to do that. But if we had a centralized location for our features that we were using, where people owned their features and they were able to be used and tracked, etc., we'd be able to consume them once and create once and use multiple times. And that's the one thing that's missing for us. And this is something that we're evaluating. How can we build a feature store that data scientists can use? So we abstract them even a little bit further away from the data sources. Obviously, they're still going to have to deal with them because the data scientists are going to be the people that are creating the features. But we want to be able to socialize and create a centralized feature store, because right now it all sits within our code, or it sits within kind of like a document, like a living document on Confluence or whatever, of features that are being used. So that's one of the other missing things. And that's me. That's kind of everything that we're doing. If you're interested in any of the things that I've spoken about, please reach out to me. You can use my Gmail, LinkedIn. If you're interested in anything that we're doing here, let me see if I can move my face out the way here. You can see everything that's been on our ABSA open source software. Please contribute if you would like, and it would be very, very helpful for us. And I think it's all about building a community, right? So we're putting these things out into the world, and we're hoping that people will catch on and say, there's a need for this in my organization, and we can kind of create this ecosystem of tools for kind of furthering, I guess, the machine learning operations or ML ops space. So thank you very much, and I hope you enjoy the rest of the conference, and I look forward to seeing you all online. Thanks.